what I gave you as your warm-up was a two-sided copy of both the notes and the homework so that you can be sure, thank you, so that you can be sure to have all the information you need. Hey, this is a really important conversation that I put at the top of the notes. So if you watch the video, it kind of went through because what ends up happening, and today we're going to be putting all of this together. Grace and I were talking earlier, and this is one of the hardest units to teach because once you get it, it all makes sense. And to me, it feels like just one lesson's worth of conversation because it's also overlapping. If you don't understand it, it feels like banging your head against a brick wall because things start to get very tangled up very easily. And the most important thing is that you really need to keep straight whether you are talking about or looking at a graph of your original function, your derivative, or your second derivative. Because each of the graphs is different, and each of the values of the graphs tells you different pieces of information. If the value, the output value of your derivative is positive, that means that your graph is increasing. If the derivative value is negative, that means that your original graph is decreasing. And if you have a 0 as the output of your derivative, that's where you have a critical point. And your critical points determine your mins and maxes, your extrema. So your critical points, not only is it where my derivative is equal to 0, but it's also where I can't take my derivative. So if my function is continuous but not differentiable, there's a sharp point in there somewhere. If there's a sharp point, I can't take a derivative at that point, but this still might be a critical point. When we moved into our conversation about the second derivative, and we talked about the second derivative when we talked about position, velocity, and acceleration, we dabbled in playing with the units, where we're talking about your, copies per minute, where we were looking at, was your derivative value getting bigger or smaller? How was it changing? So if your derivative value is increasing, that is because your second derivative is positive. If your second derivative has a negative value, that means that your derivative value is decreasing. And the confusing thing about this is when we talk about concavity, we can divide up or concave down into 4 different conversations. So if I'm talking about these 4 different conversations, we can talk about whether I'm increasing at an increasing rate, whether I'm increasing at a decreasing rate. So this is the first half of a concave up graph. The other half is here. So if I talk about this graph, my original function is decreasing. It's getting smaller and smaller and smaller. But my derivative value is increasing. It's getting bigger and bigger and bigger. It starts on negative, hits 0. So in both of these instances where I'm concave up, my derivative value is increasing. My function's increasing, my function is decreasing, but my derivative value is increasing and getting bigger. So we need to be super careful about whether we're talking about our function or our derivative. When we talk about concave down, this is the other half of this concave down graph. My derivative value is getting smaller and smaller and smaller because it's getting steeper and more negative anytime I'm going down the number line. So my graph is decreasing and my derivative value, the slope of my tangent line, is getting smaller and smaller and smaller and smaller and smaller. So up top here on top of those notes, I just put that quick synopsis, hoping that that would clarify a few things. So between this lesson and today's lesson, it's more conversations about the second derivative, and that just adds a layer to what we're talking about when we're looking for our inflection points, our critical points, our mins, our maxes, our end behavior, and whatnot.
Do you have any extra music?
Sure. Oops. Anybody else need one while I'm digging? I'm good. Kara, do you need the homework too? This one is very nice. There's no loss too. Okay. Go.
I don't get why the introduction point starting X would be negative 0, like the ones that we have written.
Yes.
I don't understand why, because those are when X equals 0, right? Or,
Okay, so that's the other conversation. So Isabel's asking a great question. I'm gonna back her up for just a minute. The other thing that we need to be super careful about, and Jaden asked a question during the quiz that where I was kind of like, oh snap, I need to be better about this, is when we're talking about locations on the graph, we need to make sure that we're talking about the X value and not necessarily the coordinate point. Because if we're talking about an input-output value, this distance on the X value across is absolute. At X is equal to 1, this is happening. At X is equal to 0, this is happening. But that ordered pair might be different whether we're talking about the graph or the derivative or the second derivative. So we need to be super careful about what we're talking about is our output value given whatever input value. Does that make sense? All right, so Isabel asks, I'm curious about these inflection points. These don't necessarily make sense to me. So listen while we go through this and see if this makes sense. Do you understand that when my tangent line has a slope of 0, that's a local min or max? Okay. So what ends up happening is if I were to graph or to look at my derivative values, here my derivative is negative. It's getting smaller. It's getting larger and larger and larger and larger, which takes me from negative to positive. It's getting larger, 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 larger still. So from this asterisk to this asterisk, my slope of my tangent line, my derivative value, is very negative. It goes to 0 and continues to get positive. So it's increasing. Are you okay with that conversation that my derivative value is increasing? Because it's getting bigger and bigger. Once it reaches this inflection point, once it teeters here, because you think about it, if it followed along the same path, it would continue growing like that. It doesn't. It changes gears and now starts getting smaller. This is a steeper value than that. This is a higher value of my tangent line than that. So at this point here, that is where my tangent line, instead of continuing to grow bigger and bigger and bigger and bigger, starts to change direction, and now it's getting smaller. So that inflection point is where my second derivative value stops getting bigger, and it starts to get smaller all the way until it hits 0. So as my change is happening, where my derivative is now decreasing, that's where I switch concavity. I switch from being up like a cup to being down like a frown. And that's where that bend, that change happens in my direction. Does that help? So that happens just like this happens, where my minimums and maximums are where my slope of my tangent line is equal to 0. That's my critical points. Where my second derivative is equal to 0, that becomes my inflection point. And that's what this lesson was all about. This lesson was where we looked at where things were increasing and decreasing. And notice we had something very similar to this when we were talking about our function and our derivative. Now we're talking about our derivative and our second derivative. So our inflection point, not our critical point, our inflection points are where my derivative changes from increasing to decreasing, and my second derivative hits 0. So I'm making the same charts as I was before, looking at, here's my original function, here's my first derivative, here's my second derivative. And it all depends on what they're asking me. Are they asking me about critical points? Then I set this one equal to 0 and solve. Are they asking me about inflection points? Then I set this one equal to 0 and solve. Once I get those critical points, then what I'm looking at is what happens on all the spaces in between. What happens leading up to it? What happens between them? And what happens after them? Because I know at them, my second derivative is equal to, the output is equal to 0. Now, if I were graphing my second derivative values, this would be on the axis. But if I were to graph this graph, not the case. At this value, my inflection would change. Does that help? Okay. So in example 1 and 2, we took our original function and we took the derivative once, we took the derivative twice, and then we were able to figure out the sign of the increasing and decreasing intervals. And again, now that we're looking at the graphs, we want to make sure that we recognize that if my derivative is positive, so this is the graph of my derivative. The number one thing, we actually ended up throwing out a question on the graph. The reason why you don't have your quizzes back is because when Ms. Holloway and I sat down to grade them this weekend, we're texting each other, and we're like, none of my kids caught, very few of my kids caught that the graph on the bottom of the first page was a derivative graph. So a lot of your answers were as if it were the original function graph. So when it comes to looking at these, so we decided to throw the question out. Throw most of the question out. Instead of it being worth 6 points, it was worth 2. So the people that got it right still get credit for it. Okay, bygones. But we really need you paying attention to what are you looking at. Here I'm looking at a graph of the derivative. Whenever the derivative is positive, my function's increasing. Whenever my derivative is negative, my function's decreasing. This is not the graph of my function. So this here, where I have a derivative value that's output is 0, this is a local min or max. So if my derivative value is positive and it goes to being negative, this is a max. If my derivative is negative and moves to positive, that's a min. Here, if my derivative is positive and stays positive, this isn't anything. It's got to cross through the axis in order for it to be a min or a max. So here is where my function is decreasing. Here is where, now this I'm looking at my second derivative. Because from here to here, my derivative value is getting smaller. That is where my function is concave down. Because from an x value of 1 to positive 1, my derivative value is increasing. This is where my second derivative is positive. The slope of this line is positive. So my function's increasing. And it's concave up. Here it's decreasing. and here it's increasing. So it's possible for me to have that point of inflection. And this is where you get one of those conversations in your graph where you have this positive concavity and this negative concavity. So that's that point of inflection. It's never a min or a max. See how I have a positive derivative that's getting smaller? Then I have a positive derivative that's getting bigger. So what's happening in green is what this story is right here with this quadratic shape. For example 4, as we go through and talk about, now be careful, again, you're looking at your second derivative graph. Anytime it's positive, that means that my derivative value is increasing. So here we're just looking at, here my derivative value is increasing, this is positive. Here my second derivative is negative. Here my second derivative is positive. Here my second derivative is negative. And each of these points where my second derivative is equal to 0, my output is equal to 0, those are our inflection points. So what we wanted you to look at here was how can you use the first derivative to find the information about a function's concavity. I need to look at whether my first derivative is increasing or decreasing. So I need to look at whether it's increasing or decreasing. If I'm looking at concavity for my second derivative, I have to look at, is my second derivative positive or negative? So this is, how is f prime of x changing? And these are always your two conversations that you're having with yourself. Am I looking at a positive or a negative value? Or am I looking at an increasing and decreasing story? I see a question here, Jacques. You had a question? Any questions on the notes? All right. So what I want you to do now is I want you to take out the homework. You have a key in front of you. And the truth is you learn nothing out of copying my key. So if you have it finished, check your work. If you don't have it finished, try some. So try to do it so that you are looking at finding the derivative. Now with some of you, the sticky spot here is you're still rusty on finding derivatives. So we have to figure out a way to make sure that if you're still struggling with finding derivatives, be vulnerable to your classmates and just say, hey, can you help me do the derivative of this one? Because it's not easy to learn it. Yeah. Let's get everybody talking about it, then we'll come back to questions. Is that okay? All right. Stephen, I don't know if I have any more. Oh, are you going to the bathroom? Quick. Our whole idea, are you with me? Our whole idea for this class is to draw the connections between your original function, your first and second derivative. Looking at how they're all related and how we can use that information to sketch curves. All right, so using the figure below, complete the chart by indicating whether each value is positive or negative or 0 at each of the indicated points. So take a note of what you have. Here is your original graph, f of x. So if we have this graph here, that is, and I'll make it darker for you, increasing and decreasing with lots of fun features and things going on. And what it says is if it appears to be a point of inflection, assume it is. If it appears to be a min or max, assume it is. So here's where A is, B, C, D, E, F, G, H, I, and J. With your group mates, please, fill out the chart. Whether your original function, your derivative, or your second derivative has a positive or a negative value on your mark, set, go. Let's do the first one together. Are you ready? Let's take a look at sweet old point A. The output of my original function is negative. Thumbs up if you agree. The slope of my derivative, the slope of my tangent line or my derivative value is positive. Because this is where my function is increasing. If I look at what's happening to my slope of my derivative, it's pretty steep, but it's going to be getting what? It's going to be getting flatter and flatter and flatter. So my second derivative is going to be negative because the value of my first derivative is decreasing. Are you okay there? Let's talk about B. Is the output of my function positive or negative? Of my original function, my output's positive because I'm up in this quadrant. That's a positive x value. Make sense? Is my derivative value, the slope of my tangent line, positive or negative? That is also positive. What's happening to the slope of my tangent line? Is it increasing or decreasing? It is getting smaller and smaller and smaller, which means my second derivative is negative. Let's talk about C. Is my original function positive or negative? My output is positive. Is the slope of my tangent line positive or negative? What is it? Negative. It's negative. Now we have to ask ourselves here, what's happening to the slope of the tangent line? Here it was 0. And here it's getting more and more and more and more and more negative, more negative, more negative, more negative, more negative. But what happens right when I reach C? What is happening to the slope of my tangent line? It switches. It switches from decreasing to increasing. See right here, it's like a little teeter-totter. So because my C is where my first derivative changes, C is going to be a point of inflection. That's an inflection point. All right, let's talk about D. What is the value of my function at D? Talk to me about my derivative. So D is going to be what we know is a critical point, and our critical points determine where we have local mins and local maxes. And I know that it's a local min because my derivative goes from negative to positive. Do you see how that happens? Now, answer me this. Is my derivative getting bigger or smaller? It's getting bigger, which means my second derivative is, with your group mates, continue talking your way through the function and your market set go. We want to make sure we know that you know what it is that you're looking at. This is the graph of your original function. And all of our conversations about derivatives and second derivatives are solely for the purpose of understanding this graph. So So as my graph is increasing, decreasing, increasing, decreasing, and increasing, those were Algebra 2 and pre-calc conversations. Now we have the evidence to support what it is that's happening. If I have a positive slope to my tangent line, then that means that my graph is getting bigger and bigger. If that slope changes from increasing to decreasing, that is that inflection point. And those inflection points I have happening at C, I have happening at E, I have happening at G, but not J. How come? Why not J? Because I don't see it changing. I see it continuing on along its same path. Any place where the slope of my tangent line is going to be 0, that is my local mins and maxes. So I have a horizontal tangent line between B and C. I have a horizontal tangent line at D. I have it at F. I have it at H. And that is where I have those local mins and maxes. So at the places where my f prime of x is equal to 0, that's what determines a minimum and a maximum. At the places where f double prime is equal to 0, that's where I'm looking at a change in concavity. All right, let's take a look at the next one. Place the values of f of x, f prime of x, and f double prime in increasing order for each point on the graph of f of x. If the point appears to be a min-max or a point of inflection, assume it is. So I'm going to say that here is my value, my x value for A. Here is my x value for B. And here is my x value for C. So when we place the values of f of x, f prime of x, and f double prime for each point, we're going to be looking at just A and their 3 values, just B and his 3 values, and just C for his 3 values. So let's talk about A. Is f of x positive or negative? F of x is negative. Let's talk about f prime of x. For A, positive, negative, or 0? 0. Let's talk about f double prime of x. Is this graph concave up or concave down? Concave up, which means this is a positive value. So when they ask me to place the values in increasing order, my f of x value is my smallest. My f prime of x value is going to be my next biggest. And my f double prime of x value is going to be my next biggest. If you'd like to write it as a mathematical equation, you can talk about something like this. Let's discuss B. Is my original function positive or negative?
Negative.
How about my derivative function, positive or negative? How about my second derivative value? So when we put them in order, my f of x value is going to be the smallest, then my double prime value, then my derivative. Talk about C in your group. Go. How did we do? Did we match? Keep in mind, these are different output values for each of these different input values. In fact, if I'd wanted to, I could have put f of a, f prime of a, f double prime of a. I could have put f prime or f of b, f double prime, f prime, and I could have put f double prime of c. So even though my input values are all the same, my output values, whether I'm talking about my function, the derivative, or the second derivative, are a little bit different. Are you with me? All right, let's flip over. With your group, brainstorm, list features of graphs that you know to look for when finding critical points, extrema, and inflection points. Fill the box on your market set, go. When we talk about this, we're going to start sketching the derivative given a graph. And we're going to use a lot of those critical points or points of inflection, mins and max, to help us out. All right, so let's take our original graph and let's talk first of all, what kind of a graph is this first section from infinity up to x is equal to 2? What's happening there? I'm looking for, it's increasing at what kind of rate? Yeah, it's increasing at a constant rate. So that slope looks like it's a rise 2, run 1, rise 2, run 1. So if my slope of my linear equation is positive 2 over 1, from negative infinity all the way up until a value of x is equal to 2, the value of my derivative is 2 because it's increasing at a constant rate. So what's my derivative value here? 2. What's my derivative value here? 2. What's my derivative value here? Here, here, and here? It's all 2. Are we okay with that? So now let's talk about the second half of this. I'm not going to be able to take the derivative here. How come? Because it's a point. So in fact, if I go to show you what the derivative looks like, a slope of the line that touches it once, is it here? 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 Because there's this sharp point, I can't say. But I get to a point of where my derivative is suddenly negative. Is it a little negative or a lot of negative? Is it steep or flat? It's flat. It's a little negative, right? So suddenly down here, my graph isn't 0, but it's just below. Now what's happening here? It's getting steeper and steeper and steeper and steeper and steeper and steeper. Does my derivative ever stop being negative? So the interesting conversation is, if I have a straight line, my derivative graph is 0. If my original graph is quadratic, my derivative graph is going to be linear. If my derivative graph is cubic, my derivative graph is going to be 1 power less. So when I look at each of these combinations of graphs, I know that sketching the derivative graph is going to result in a graph that has 1 less turn in it. All right, let's take a look at this graph. graph of a function is shown. Let's sketch the derivative graph. So let's talk about some things that I know are super important. If I look at this, and this, and this, what did I just draw with my red pen? The place where it's a critical point. It's a place where what? The slopes are equal to 0. Veronica says, I agree. That is the place where the slope of my tangent line is equal to 0. So that means that at negative 1, 2, 3, the slope of my tangent line is 0. At 0, the slope of my tangent line is 0. At positive 1, 2, 3, the slope of my tangent line, 0. What's going on with my tangent line here? Am I positive or am I negative? Am I positive or am I negative? I'm positive, and I'm approaching 0. What's happening here? What's happening here? I have a 0 slope, and then what's happening? My slope is becoming negative. It's becoming negative, more negative, more negative, more negative, more negative. What do you think happens right around here? It stops becoming negative. If it were going to continue going negative, wouldn't it continue going like that? But it ends up turning around. So if this is my inflection point right here, this is where I must have a derivative equal to 0. Do you see another inflection point where I go from an increasing slope? Where I change directions? Do you see another inflection point? So somewhere between 1 and 2, I'm going to again have where my second derivative is equal to 0. This takes me all the way up to here where my derivative is equal to 0. And what happens here? It becomes negative, and it does what? Continues going down forever. Do you see a 4th degree graph become a 3rd degree graph? And that is because what I pay attention to is when f prime of x is equal to 0. I pay attention to when f double prime of x is equal to 0. These are critical points, and these are inflection points. All right. So you're sitting in groups right now, and I'm going to ask Grace and Nadia to come on up and join Nate. You guys are sitting in groups of 3 for the most part, that's fine. Would you please send one person up to get whiteboards, one for every person? Send a second person to the back to get markers and socks for everybody. And send the third person to get a game. So here's what you're going to do. Take this first ticket off because these are your instructions. And that's going to tell you all the things that you can talk about or think about when it comes to each of these graphs. So the easy conversations are, is the graph continuous? Is the graph differentiable? So those are going to be your first couple conversations as a group. You're going to rotate around, and whoever is the card picker is the one that's the card leader, and he's going to lead the discussion. So is the graph continuous? Is it differentiable? You can look at the graph and prove whether there's absolute or relative extrema, whether there's an absolute maximum, an absolute minimum, local min, or local max. You can have those conversations. All right. Then you can talk about intervals where the graph is increasing and decreasing, and then you can talk about points of inflection. What I want you to do on your graph is I want you to graph this, I want you to sketch the graph of the derivative. So I want to remind you of a tool that is in your Schoology, and that is this derivative tracker where you can enter in an equation and then run that slope of the tangent line along that equation, and you can look at the derivative. So what you are going to be doing in this game is sketching what the derivative looks like. Notice here how it changes. Concavity right here is right where that derivative value has a slope of 0, and you can watch that go. So this website is on your Schoology, and you can go ahead and change this. If we have a quadratic equation, we can go ahead and graph. Notice my derivative graph becomes a straight line when I have a quadratic. So your job for this game is each of you sketch what the derivative graph looks like for that graph on your boards. Questions? All right. So the person that is sitting closest to the door is going to lead our first discussion, and then you're going to go around to the left. Make sense? All right. And Marcus, back up.